1. Good morning, everyone. Welcome to the Toronto Geometry Colloquium, Season 2. This is a weekly web series all about geometry processing.
And this colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. And every week, we will have an opener talking about their cutting-edge research for 10 minutes, followed by the headliner give us a keynote presentation.
And as usual, if you have any questions, please just feel free to leave comments on YouTube live chat or join our Discord channel to get involved in the discussion. And today, I'm thrilled to introduce our opener, Michal Piovarči. Michal is another speaker that we have from Europe, and he is currently a postdoc researcher at IST Austria in the Computer Graphics and Digital Fabrication group led by Professor Bernd Bickel. And he just obtained his PhD at USI Lugano under the supervision of Professor Piovarči in 2020. And his research interests include computer graphics, computational fabrication, haptic reproduction, appearance reproduction, and perception. And recently, Michal and his colleagues are going to launch a web seminar, which is all about computational fabrication. And I encourage you to check out their website for more details if you are interested in fabrication in particular. And today, Michal is going to share his latest paper, which is called Towards Spatially Wiring Gloss Reproduction for 3D Printing. And let's welcome Michal.
Okay, thank you very much for the kind introduction. And good morning in Toronto. I am Michal.
Michal, yeah. We see your presenter screen, not your
I slide. See. But it was telling me it's the other way around. I'm sorry. Okay, better now?
Yeah, that works.
So I would like to talk today about our project, which is called Towards Spatially Wiring Gloss Reproduction for 3D Printing. And this was a collaboration between UC Lugano, MIT, Max Planck Institute, and Princeton University. And the color and gloss of an object are some of the most salient features and are crucial for their visual appeal. And careful use of gloss variation is used in oil painting to create more vivid and saturated colors. In manufacturing processes, the surface finish reveals fabrication defects, and a carefully polished smooth look is associated with a high perceived value. Moreover, the reflectance of an object can have a functional use in directing light towards desired regions, like this piece from a cinema projection screen that reflects lights only towards the audience. And the importance of surface gloss drives a significant interest in designing systems that can reproduce objects' appearance. One possibility to replicate target appearance is to spatially deposit materials, which are then locally averaged by the human visual system into convex combinations of colors. An alternative approach is to deter only the diffuse color and modify the reflectance by optimizing surface geometry to reflect light to desired directions. And these two approaches can be combined into a method that uses both materials and geometry to replicate the target appearance. Unfortunately, while commercial printers can produce colored prints, they offer only two finishes, glossy and matte. And this for two reasons. If we use various materials to affect the appearance, we will couple the color and gloss reproduction. And this is undesirable since due to the material properties, reproducing color is generally possible and desirable at a much higher resolution than gloss. And on the other hand, geometrical approaches to gloss modification are infeasible due to the hardware constraints, since the supporting material erodes the surface and destroys the optimized microgeometry. So inspired by these practical limitations, we seek a different system. We propose to decouple the color and gloss manufacturing by first using a high-resolution process to fabricate the color information, and then a lower resolution process to fabricate the gloss. When combined, we achieve a full appearance reproduction. And since core printers are commercially available, the main challenge here lies in gloss fabrication. To this end, we propose to use off-the-shelf varnishes. These materials are ideal for two reasons. They affect only surface reflectance and allow for creating a wide range of finishes from glossy to matte. Unfortunately, to create a matte finish, varnishes rely on incorporating relatively large particles that make the material more viscous. And these two components, high viscosity of the material and large particle size, make the material infeasible to jet on commercial 3D printers. So we tackle this issue by proposing a novel jetting apparatus capable of handling highly viscous materials like varnishes. And to enable production of spatially varying gloss, we provide guidelines on how to characterize the gloss gamut from our device and equip it with a predictive model that enables converting target gloss into a spatial varying mixture of varnishes. And this combination of hardware and software enables fabrication of high-quality spatially varying gloss. We will start by describing the inner workings of the hardware apparatus, crucial for the software design, and continue by quantifying the achievable gloss gamut. So the apparatus consists of a Cartesian robot and a printing head. And the key feature of the printing head are the three piezo-actuated needle valves. A needle valve consists of a pressurized material reservoir, and the material goes through the valve body until it is stopped at a needle valve. The valve is controlled with a piezo-actuated spring that moves it up and down to release material through the nozzle at the bottom. During a typical operation, the valve starts closed and blocks the passage of material. When a signal is sent, the valve opens over a desired time interval for a specified height. This allows the material to escape. When the valve closes, the needle impacts the released material and jets a droplet. And here you can see some exemplar droplets from various varnishes that we have used in our experiments. To quantify the gloss gamut of our manufacturing process, we built a reflectance measurement device. We place our varnish sample on a black cylinder and illuminate it with various point-like sources. The luminance is then captured by a camera as an HDR image. And here you can see some example captures of varnishes from various manufacturers with various levels of gloss. To better appreciate the highlight, the point like this is replaced with a line illumination, and that's why you see a line directly through the middle of the varnishes. Using our measurement device, we extracted the luminance of all of our varnishes, and here you can see example raw capture data for a matte, satin, and glossy varnish. The x-axis on the plots represents the deviation from a mirror reflection, and the y-axis the luminance captured by our HDR camera. Next, to avoid the gamut of achievable gloss, we fit a one-lobe Cook-Torrance model with GGX distribution, which, as you can see, achieve an excellent match to the measured data. And it also allows us to visualize our varnishes using a physically based renderer. Using our phenomenological model, we can plot the gloss gamut of our varnishes. Here, the x-axis is the roughness that encodes the width of the specular lobe, and y-axis is the Fresnel factor that governs the intensity of the specular reflection. For qualitative evaluation, we add different materials to the gamut: transparencies, varnish plastics and papers, oil colors, so on and so forth. We can see that on one extreme, we can create a glossy finish on par with a transparency sheet. On the other extreme, our varnishes are quite matte, on par with varnished papers, but we could still use an even more matte varnish to capture the range of oil colors. And since our device is limited to print only with 3 materials at a time, we need to select a subset of these varnishes that will best cover the available printing gamut at a given time. And for the varnish primaries, we consider our glossiest and mattest varnish respectively. And for the third varnish, we use a satin material. By incorporating an in-between material, we can better handle the artifacts inherent to special mixing of varnishes, which we will see later. And with our selected primary varnishes, now we can turn to the software part of our gloss printing system. So we wish to design a predictive model that, given a desired reflectance, gives us a spatial map for half-toning. To design such a system, we cannot rely on our Cook-Torrance model since it assumes single-lobe PRDFs, and after juxtaposition, we create materials that have 3 distinct lobes. So therefore, we decided to not impose any assumption on the measured data and base our system on predicting the raw measurements of convex combinations of varnishes. More specifically, we use a simplex interpolation model. The corners of the simplex are formed by selected varnish primaries, and to model the nonlinearities introduced by physically jetting materials, we tessellate the simplex and physically manufacture and measure each sample lying on a tessellated vertex. When we want to predict the appearance of a new mixture, we start by locating the approximate tessellated patch using barycentric coordinates, And based on barycentric coordinates from within the patch, we interpolate the raw measured data. And this leads to a full prediction of the measurement that we would obtain from this new varnish mixture. We have validated our model in cross-validation and achieved excellent predictions when leaving out different varnish mixtures. The largest discrepancy was observed when leaving out highly concentrated mixtures of glossy varnishes, and this is due to the high nonlinearity of mixing glossy varnish with more matte variants. However, this is not the full story. Unfortunately, reproducing the raw reflectance is not sufficient to match the appearance of gloss. Since our materials are juxtaposed, an observer can potentially see the dithering pattern. And this is very similar to the skin of a citrus fruit, that when we look at it, we see visual bumps. And for this reason, it is known as the orange peel artifact. And to avoid this artifact and combat it, we leverage the fact that not all dithering patterns have the same visibility. Thanks to incorporating a third varnish, our system can generate multiple combinations that have the same or similar appearance in terms of BRDF, but drastically different dithering pattern visibility. As we can see here, a 50-50 mixture is visually undistinguishable from a pure material. And the intuition behind this effect is that while in our input we assume that jetted varnishes are square, in practice they are circular. And this causes physical mixing between the varnishes at the boundary, and if the varnishes are close to a regular grid, the physical mixing can completely mask the presence of a dithering pattern. So we leverage this fact to quantify the visibility of dithering patterns. To estimate the visibility, we start with the dithering pattern and split it into individual components for each varnish, which we turn into black and white masks, and blur them with a 1 pixel Gaussian filter to mimic the spatial mixing of varnishes. Finally, we quantify the remaining variance by computing the standard deviation of the values inside the individual patterns. We evaluate our predictor qualitatively by observing that the ordering given our predictions correlates well with captured dithering artifacts. And in practice, our predictor helps to remove the noise inherent in dithering, which minimizes the orange peel artifact, since our generated dithering pattern is smoother. Now, I would like to show you the results of our proposed gloss manufacturing system. We start by evaluating the gloss range achievable by our setup. To this end, we created a gradient of gloss that we capture with a camera in the mirror reflection of a screen displaying a checkerboard pattern. You can see that we have achieved our goal, and our system is capable of smoothly interpolating from matte to glossy appearance. Next, we evaluated our measurements and the predictive model for the evaluation of we created flat samples with spatially varying gloss, and the samples were captured with a camera located in a mirror reflection of an area light source. And here you can see the input gloss map that was deterred using our algorithm, and our prediction with rendering that uses the phenomenological models of the base varnishes in a physically based renderer. Since the camera is set in the mirror reflection of our light source, the glossy regions appear white because they reflect more light towards the camera. And finally, the physical photo capture that achieved excellent match with the simulation. For the last evaluation, we check how our setup is capable of reproducing target appearance. To specify the reflectance, we use a standard physically based material commonly used in movie and gaming industry. The reflectance is described as a Cook-Turns model with GGX distribution and consists of 3 maps. The diffuse color is defined with an albedo map, and the surface gloss is a combination of roughness and metallic maps. To reproduce the appearance, we manufacture the albedo on an inkjet printer and utilize the roughness and metallic maps as input to our pipeline. The desired gloss is then transformed into a dithering pattern that is applied on the sample using our printing apparatus. To observe the spatial gloss variation, we capture the manufacturing pieces with a light that orbits the samples and a camera which is located at the same elevation angle. And here we can see an example of a floral pattern where we manifest uniform reflectance across the surface for the direct printout, whereas in contrast, our post-processed materials have spatially varying gloss, and this effect is visible in the metallic flower ornament that is significantly glossier than the matte wood outline. So to conclude, I have presented today a full system capable of creating objects with spatially varying gloss by depositing varnishes. To enable production with such challenging materials, we propose custom printing device capable of jetting highly viscous materials. We characterize the device from hardware setup to identifying the effects of printing parameters on droplet shape to gloss gamut estimation and selection of varnish primaries for printing. We support the printing device with a predictive model that estimates the reflectance of varnish mixtures, and to minimize the visibility of dithering patterns, we propose a quality metric inspired by the properties of human visual system and physical mixing of varnishes. And we have shown how this all can be together applied to manufacture objects with desired reflectance. So thank you very much for having me.
Okay, thank you. Thank you, Michal, for the great talk. And as usual, we'll move on to our headliner. I have a joint Q&A session in the end. And I have to say, it is my great honor today to introduce Professor Dave Levin. And part of the reason is that by featuring him, we finally put Toronto into Toronto Geometry Colloquium. But in case you don't know him already, which I assume won't be the case, Dave is an assistant professor in the Department of Computer Science at the University of Toronto. Although he's currently working from the satellite campus located in his basement. And during the pandemic, he has two cats who are currently helping him give the lectures if you follow his simulation course online. So I'm very glad today that we actually have him to give this talk in person. And his main research interest is using new simulation techniques to allow artists, engineers, and scientists to study and create everything from animations to machines. And before he came to Toronto, he was an associate research scientist at Disney Research and a postdoc with Professor Wojciech Matusek at MIT, and he received his PhD in computer science at UBC with Dinesh Pai. And today, Dave is going to share his insights into a glitch in the matrix, the surprising weirdness of physics-based animation. And let's welcome Dave.
All right, hello everyone. Sorry about that. I completely forgot how Zoom worked for a minute there. So this is very exciting to me. It's a big honor for me to get to come and talk at the Toronto Geometry Colloquium. I was looking jealously at the names that were appearing on the list and thinking, when will it be me? And that time is now. So great for me. We'll see how you guys feel about it in the end. Before I get started, I want to give a big hand to Michal Piovarči, the opener. I've worked with Michal a little bit, and Michal has really won me over to the idea that perceptual science is a big missing component in computer graphics. So YouTube Live, whatever you're doing out there, maybe we can give one awkward internet round of applause to Michal for just a fantastic job. All right. I also want to thank the true hero of this session of the TGC, which is Genevieve Ashley, this week's artist who created this unbelievable poster, which I think includes a perfect reproductions of Michal and myself. I don't know what the likeness rights for this thing are, but I want to use this image on everything from my driver's license to when I'm introduced from talks for forevermore. Means I can never cut my hair again, but I think I'm okay with that. So I think this is a bit of a different TGC because, spoiler alert, I'm not really a geometry processor. I mean, sure, I occasionally get tricked into doing some geometry processing. I had a recent collaboration with Michael Tao, University of Toronto PhD student, where we made cut cell meshes, lots and lots of cut cell meshes. This is just a fun selection of thousands of meshes Michael made for this paper. But for me, geometry processing has always been a necessity. And it's a necessity which enables me to work on the thing that I really love. And since I started my master's in, actually, I can't even remember when, that's been physics simulation, and specifically, the mechanics of deformation. There's just something about the life that simulations can breathe into even the simplest geometries that I just can't get enough of. And so in this talk, I wanted to spend a bit of time sort of spreading that love around, while simultaneously peeling back the layers on some of the surprisingly infuriating behaviors of algorithms for simulating motion and deformation. And I'll talk a bit about some potential fixes, and hopefully I can convince a whole bunch of the smart people watching this that, this is a fun problem and that we should all be doing more physics simulation. All right, well, why am I doing this? Well, my enthusiasm for simulation sort of has its roots in an artifact from my childhood. When I was younger, I spent an inordinate amount of time playing games like this. So this is King's Quest I. It was released in 1984. Yes, I'm a fossil, but I'm still considered somehow an early career researcher, which is fantastic. And this was an early adventure game that sort of tossed you into a small fantasy world in which you could explore using a text-based interface. And at first it felt almost magical. You could ask to pick up objects, look at them, ask what color they were, and you would get an actual response. But it didn't take really very long to find the boundaries of the allowed interactions. And it's obvious why. Every interaction in the world had to be programmed, and it's impossible to handcraft all of this stuff. You know, even if the world that you're handcrafting it for is little, like the Kingdom of Daventry, which was the kingdom in King's Quest. But you know, what I didn't know when I was 6 years old playing this game is that a potential answer would show up at SIGGRAPH in 1987, and that was the elastically deformable model. And this is sort of widely recognized as the first paper to propose using physics for computer animation. And actually the results are pretty amazing. So if we look at this video from the actual paper, this paper already had all of the things that we like to talk about in physics-based animation, or most of them at least. It had volumetric simulation, it could do cloth, it had, you know, sort of what has become like our standard mathematical variational formulation. It had penalty force collisions, all in 1987. If you're at all interested in this field, you owe yourself to read this paper just to kind of see how forward-looking it was. But perhaps the most important thing of this paper is its vision for the future of physics and graphics. So Dimitri Terzopoulos, the first author, points out that what he calls active models can produce realistic, diverse interactions simply by implementing the rules of physics. In other words, we could be free from hand coding or hand animating every possible interaction between objects in a virtual world, and we can get their correct behavior, or their correct behavior will just emerge from the physics. And I think this is a really inspiring notion. In my mind, it's still the reason to explore using physics in computer graphics. And it gets even more tantalizing when you consider that many of these interactions are consequences of solving a deceptively simple looking ordinary differential equation, Newton's second law. Newton's second law describes the relationship between the mass of an object, its acceleration, and its applied forces. It's compact, but it yields this beautifully complex motion, and it sort of teases us with the idea that realistic, all-encompassing emergent behavior is just two applications of time integration away. You know, just two time integrations to escape from the hard-coded universe of King's Quest I and into sort of a fully simulated, realistic environment like those people have been imagining in science fiction for decades now. Just two applications of time integration to being able to manufacture safer cars, faster trains, better spaceships, the whole 9 yards. So there's this massive, exciting promise for the technology. But somehow every time I sit down and try and use it for something, even simple things, I discover or learn about some odd behavior or glitch. And in fact, most of my research is just patching up these glitches. So let me show you an example. This is a really simple simulation or setup for a simulation of a square piece of cloth being pulled over a table edge. So this test is inspired by the fact that in most cloth simulation papers, you see a gorgeous example of cloth being tracked over a nice smooth sphere, and it always looks great, but somehow never really sharp edges. And so myself and Nick Wider and other collaborators on this paper, we thought, well, let's try this and see what happens. So when we do try it, we notice something weird. There's kind of like an unseemly jittering to the interaction. Let's look at that again. And this time, you know, we can focus on what's happening inside the green square. So you can see that there's this funny bouncing. Now, I don't know about you, but my tablecloths aren't doing this at home. It's weird, right? It's a weird artifact of the simulation. So we did what any self-respecting researchers would do. We asked around, and yes, it turns out that this was sort of a known issue with cloth simulations. The mesh just gets snagged on sharp features, and it's actually been that way since Terzopoulos' original paper in 1987. And it's a problem because it's not the expected behavior. If you're an artist or a practitioner and you're using these algorithms, this would perturb you and you would have no idea how to fix this, right? It sort of messes with your conception of how the world could work. Okay, let's file that away for a minute and let's look at another example. So anyone who has seen a physics-based animation paper knows that we just really love to simulate rubber wiggly things. And to do this, we need a model for how rubber produces forces in response to deformation. And so we call this model the constitutive model or the material model. Now, normally, smart material scientists have measured or computed the appropriate parameters, and you can just look them up online. This is just a screenshot of Wikipedia's page for material parameters and has, everything you could ever want. And the idea is that the material behavior of our rubber ball is described by a very small number of these material parameters. And again, this is the power of physics simulation, right? Complex behavior from simple models. Now we look up the value for rubber and let's simulate something. So here we're simulating pushing down on sort of two identical shapes. They're both made of identical material. They have identical material parameters, and we get wildly different results, even if we press down on them with the same force. And the only difference here is that the mesh, the simulation discretization that we're using has changed its resolution. The one on the right is lower resolution. And a funny thing has happened. Changing the mesh has actually changed the very nature of the thing itself. If you're an objectivist philosopher right now, you're freaking out. This is very upsetting. And so we call this numerical stiffening. And it's weird. It's totally counterintuitive unless you're sort of a finite element guru. And just in case you think that's the worst thing that can go wrong, material handling has all kinds of unexpected failure modes in physics simulation. So let's say we're going to simulate this abstract human arm. We have a soft muscle and a stiff bone, and they're connected by a joint at the elbow. And there's gravity acting on this whole system. It's pinned to the shoulder. Sadly, if we just use a standard optimization scheme to try and simulate this setup, actually, it won't even converge to a solution. So it doesn't even give you a wrong solution. It just gives you nothing. And if you use a powerful state-of-the-art method that works great for many other applications, you converge to the wrong solution. The arm doesn't move. And so the stiffness of the bone sort of is pathological and it just locks the whole system. And that's extremely weird. These odd inconsistencies are sort of the dirty secret of physics simulation. But in graphics, we can always rely on our secret weapon to fix these things. And our secret interface or secret weapon is just letting artists and graduate students engage in a kind of mortal combat with all possible parameters and variations of the algorithm in order to produce these beautiful results. And don't get me wrong, this works, right? We see evidence of this every time Marvel releases a new movie. The visual effects are gorgeous, but they're time intensive to create. And in my mind, this approach is just antithetical to the original goal of using physics in the first place, which was to free us from the expertise and effort required to handcraft all of this emergent behavior. In fact, arguably, we now need more expertise to rein in the physics, since the effect of parameters is often indirect. And I find all of this a little bit depressing. So let's try and push back towards that initial dream of complex behavior emerging from a relatively elegant mathematical model. In actuality, Newton's second law is just a model, and it's modeling the effect of basically atomic interactions governed by rules we don't entirely understand yet. So these images are scanning electron micrographs of different types of fabrics, and you can see that they have this incredibly beautiful and complex microscopic structure. And it's this structure that gives them their distinct mechanical behavior. But sadly, this is a bit beyond us to directly simulate things at this level. And so, like good mathematicians and computer scientists, we use abstractions. And in simulation, our favorite abstraction is a simplex. So if we're simulating cloth, what that means is we model this geometry as triangles, and we model the movement of cloth using the movement of the vertices. These vertices parameterize the cloth motion, and we call these the degrees of freedom of the system, the DOFs. So let's revisit our first example of weirdness, this funny chattering sliding contact. To understand one of the potential problems here, we can crack open our favorite contact mechanics book. And you'll always find, whatever book you pick, you'll find a diagram like this. And it looks so simple. There's a single point contact, and there's a degree of freedom right at that contact point. And this is a pretty good model for the real world. At any contact, there's probably an atomic piece of cloth there to push around. But, it's a bad model in the discrete world. Because, the odds that our vertices are in the wrong place, that they aren't right on the contact, is pretty high. And even if they are in the right place, the neighboring triangles kind of get hooked around the sharp edge and they cause this cloth to snag. And that's the base cause of this weirdness that we're observing. So strangely, I looked at something very similar for volumetric objects in my first SIGGRAPH paper in 2011. So here the goal is to handle this kind of extreme conforming contact between deformable objects. So originally we were going to use this to simulate muscles, but we ended up just doing bunnies and dragons instead. And what made this work is that this is an Eulerian simulation. It tracks material flow past fixed points in space. So essentially these bunnies and these dragons are sliding through the simulation mesh. Now it requires some extra bookkeeping, but the sliding effect helps mitigate these artifacts from contact and deformation. So the question is, can we import that sliding feature into cloth simulation? And spoiler alert, we can, and we did. And the way that we do this is remarkably simple and sort of like fun because it's very graphicsy. So as it stands, moving the vertices of our triangle mesh is gonna move our cloth around in the world. That's basically the standard thing that happens in cloth simulation. But what we want is to allow cloth material, here represented very scientifically by bunnies and dragons, to flow through these triangles as well. So this means that even if our triangle gets snagged on a contact, it can't move in space, the cloth material can still move around. Now, if you're a practitioner of computer graphics or it's something you're familiar with, this picture should be very evocative of a particular operation. And that operation is just changing the texture coordinates at the vertices of the triangle. And so if we add these texture coordinates to our degrees of freedom, we can enable this type of sliding. And so mathematically, once you make this decision to add your texture coordinates into your degrees of freedom, you can use variational calculus to derive the Euler-Lagrange equations. And this kind of gives you a potentially scary version of Newton's second law. So here, this Q is just all of the degrees of freedom of the system, so vertex positions and texture coordinates. And this Q dot is just the velocities. And this is really just like a more generalized version of mass times acceleration equals force. And if you've got a lot of time on your hands, like I have lately, you churn through this differential equation, plug it into your favorite time integration scheme. And we combine this with a little bit of remeshing. And you get this beautiful smooth sliding. And it just looks perfect, just like what you would expect to see. And you can even do sort of previously impossible things with this. So this is kind of a clothesline with a piece of cloth hung over the clothesline, and you can pull this back and forth and you get this nice smooth sliding. Any standard cloth simulator is going to sort of get stuck or lock up, or at least look very jittery here. And you can handle point contacts and things like this. Here's this cloth just happily sliding along. One of the things I really love about this example is that if we just look at this again and you sort of focus inside of the green square, you'll see that you get this great resolution, visual resolution of where the spike is poking the cloth. And it's exactly the sort of pattern you expect to see. And so this is an example of fixing a sort of a bug with the motion, but then for free, getting sort of an emergent improvement in visual quality. And I think that, that's sort of one of the fun things about these physics algorithms is that oftentimes by fixing the math and the numerics, we inadvertently create even more visually compelling results. All right, so what did we learn from this? Well, we sort of learned not to trust the discretization in the sense that just because something is tried and tested doesn't mean it's correct. So you shouldn't trust the discretization, at least until you've put it through the ringer yourself. And hopefully now that you're suitably paranoid, I want to revisit the second source of simulation weirdness, which was material parameters. So as we previously discussed, all simulators consume a material model, which defines how the simulated object responds to external forces. And that model is an abstraction of the underlying microscopic interactions that are occurring in whatever material you're simulating. And you look it up on the internet. And then this is fraught with peril because there's this mesh dependence. So how do we fix this? Well, my PhD supervisor, Dinesh Pai, always liked to point out that computer science is entirely abstractions. And sometimes we confuse these abstractions for what's really going on. And so sometimes you just have to go back and look at the real world. And so that's what we did. Let's say we want to measure and simulate something that's made of the same material as this wiggly object. What we can do is we can put some tracking markers on this object and we can actuate it. And then we can look at the oscillating, decaying signal that we receive by tracking those markers. Now, it turns out that there's a well-known relationship between the decay rate and frequency of this signal and the parameters for a linear spring mass damper system. And so from this simple experiment, we can compute the actual material properties of our object. However, we still can't directly plug them into a simulator because this numerical stiffening will occur and the result will be weird. So what do? Well, we can rely on an old friend, modal analysis. Modal analysis is a numerical technique that lets you take a simulation mesh and a material model and decompose it into deformation modes. These are just low energy motions that dominate the simulation. And these motions have a frequency associated with them. Our goal is to just scale these frequencies so that they match the measured value. And what's kind of nice about this is we can do a pretty good job of this by using a really simple formula. And so here we rescale the internet Young's modulus by a ratio of measured and virtual frequencies. And this gives us a brand new Young's modulus, which we plug into the simulation. And I'll show you some examples of how that works in a second. I wanted to point out that while we were working on doing this material scaling thing, we also realized that handling contact with finite element simulators doesn't work as well as we thought. So it turns out all the contacts are too bouncy. So we developed a new way to also fix this overly excited response. If you look at
that both LCP and DKE
free voiceover. So you can see if we just watch this again, you can see that our model doesn't bounce just like the real world object, and all of the other previous solutions, including ones used in graphics and engineering, introduce this extra bounce. And so if we put all of this together, we can do surprisingly exact simulations using very coarse meshes. So here we're simulating these sort of jumping mechanisms, and you can see the results of the experiment on the right. And if you've ever done any simulation, this should almost feel like it's miraculous. Like we never thought it would work this well. For reference, to get the same accuracy without adjusting simulation parameters, the simulator itself becomes 100 times slower. And so by making it 100 times faster, we could actually use the simulator to design these working mechanisms. But so we had this additional side effect of fixing what is essentially a physics problem, which is that the simulation became much faster, and then we could use it for all sorts of different problems. And so this was really nice. It was really fun. We spent hours and hours playing with various versions of these things. We did a little bit of follow-up work on this. So we've basically been refining this scaling formula. And sort of the most recent version of it for physics simulation is a thing we call eigenfit. And the point of eigenfit is now really no matter what your mesh resolution is, when you run the simulation with a particular set of material properties, the dynamic results are going to look relatively similar. This is really important for artists in visual effects because they often like to work with coarse simulation models because it's fast. But then it's very frustrating because you increase the resolution of your simulation model to build your final shot, and everything is different. So this is a really like important problem for them. So what did we learn? Well, again, the lesson here is you can't trust everything you read on the internet, and especially material model parameters, because there's this non-trivial interaction with the discretization that has to be taken into account. And so with all that, now you might be thinking that there is nothing else that can go wrong. And if that's the case, either you joined late and you missed the introduction to the talk, or you're like me and you were so dazzled by those jumpers that it just got blasted right out of your mind. But in either case, I have some bad news. It turns out that even if you do everything right, you use a sufficiently high resolution simulation mesh, you correct your material parameters, things will still break when we try and simulate really complicated heterogeneous objects. So my sort of go-to example of this is the human musculoskeletal system. You have squishy muscles, you have stiff bones. We can create pretty dense tetrahedral meshes of these things. And then we've already seen that even if we do that, just because of how the simulator itself works, things will lock up, right? We don't get the desired effect. We can't even bend our arms, which would be a horrible circumstance if the real world was actually running standard physics-based simulation software. So I want to show you how we fix this problem because it's another example of you doing something potentially unintuitive to fix a glitch in the system. So normally simulation meshes are continuous. And what that means is that triangles share vertices. This ensures that displacements are continuous across triangle boundaries. But that doesn't always have to be the case. Rather, you can use a discontinuous simulation mesh. And in this mesh, individual simulation elements aren't really attached. Each simulation element just keeps track of its own deformation, but it doesn't really understand how it recombines with its neighbors to make a global representation. So one of the things that you can do is you can use something like Poisson reconstruction to rebuild an approximate continuous mesh from the discontinuous chunks. And you can add the distance between the discontinuous and continuous representations to the simulation as sort of an extra potential energy. And then, we can apply variational mechanics and we can solve for these deformed poses and we'll produce, valid physically simulated results. So that all sounds, nifty. It sounds like a lot of work, but how does it solve this problem, this sort of tennis elbow that our simulated characters have developed? Well, it works because the discontinuous mesh elements can move relative to each other without deforming. And the stiff bone elements can actually then compress during the solution procedure. This seems super counterintuitive, but basically, remember there's this essentially rubber gap between all of the elements of the simulation. So by disconnecting the mesh, you add more degrees of freedom to the system, and now there's a whole new set of paths to get from your initial conditions to your solution. And one of these paths involves actually allowing the rigid bones to change shape. They'll go back to a rigid configuration at the end of the solve, but this additional flexibility allows them to kind of escape this initial lock configuration and do the right thing. Here, what's happening is we're activating the bicep and we're causing the forearm to bend, which is what we'd expect. And so now we can simulate more and more complicated musculature like this leg, which bends at the knees when we activate the hamstrings. And you can see you can bend it through a large range of motion, more than 90 degrees. And then you can relax the hamstring muscle and the bone will go back to its original position. We can do this for more complicated setups, like this upper body rig where we can generate motion of the arms by flexing the chest, bicep, and back. So we can really put our simulated characters in the gym now. And this is all because we sort of changed the discretization. One of the fun emergent benefits of this is that it also makes the algorithm much faster, especially for large meshes. And it scales better as you increase the number of cores in your machine. So again, chasing down a glitch ended up having these additional emergent improvements in the numerical method. All right, so what did we learn here? Well, lesson 3 is really just doubling down on lesson 1. Don't trust discretizations. Even tried and true discretizations aren't necessarily perfect, and they can have non-trivial interactions with the physics of the system that can cause issues. And oftentimes departing from the norm is the key to solving these difficult simulation problems. All right, so I summarized my takeaway messages from the talk. And this started out as sort of a story of how much I love physics simulation, and it's sort of become a cautionary tale. So that it took a sort of a dark twist. But I don't think that's where it has to end. For me, all of this is part of the great game of physics simulation research. Each simulation algorithm is like a family, and each part has to work together to get the job done. And that includes all the things we talked about today: discretizations, kinematics, material models, but also other bits and pieces like time integration, geometry generation, contact handling. And we're engaged in the great search for the perfect set of pieces to make it all work. That's just as exciting to me today as it was when I started, which is now, I think, more than a decade has passed. So, as I sort of continue to stumble across these weird glitches that arise in simulation, there are really 4 things that are on my mind, 4 things that I think we have to focus on if we really want to make progress here. The first is that I think we've reached a point where physics, especially physics-based animation, is a pretty mature field. And a lot of the problem is a systems problem. Large-scale simulations have a ton of implementation overhead. You need to map them onto very powerful computing architectures. And unlike other fields like machine learning or even geometry processing, simulation doesn't have a widely accepted framework for easing the implementation of performant code. 33 years after the first paper in the field, we still basically roll our own stuff for each and every project. You only need to look at the success of deep learning, which is fueled by tools like TensorFlow and PyTorch, to see how useful a community-wide engineering effort can be. Recently, there's some hope in terms of custom languages like Tai Chi, but it's still hard to convince someone that they need to learn yet another programming language to really get the job done. So I think when someone builds the PyTorch for physics, it's going to be a really big deal, and it'll really help push the field. Since this is the Toronto Geometry Colloquium, I should talk a little bit about geometry, I guess. I think we're getting to the point where we have pretty robust tools for generating triangle meshes and tetrahedral meshes. Things like TetWild are now a well-loved part of my arsenal for fighting with badly behaved geometry. But one thing we don't have is good tools for codimensional simulation. That's simulation of objects which have combined volumetric, thin sheet, and even rod geometry. Our current pipelines kind of force you to make a choice of which category your object fits into before you simulate it. And that's painful and it's complicated. The fact is that all the objects we simulate are inherently volumetric. It's just that triangle meshes aren't necessarily a good approximation for that. So I'm pretty excited about new meshless methods coupled with some of the new exciting efficient signed distance representations to avoid these kind of self-imposed headaches. For what it's worth, this combination of tools is starting to see a lot of use in the video game industry in order to simulate, pretty degenerate geometry, and the results are really, really promising. I think it's a long road to wean people off of the simplicial complex, but it's certainly something that I'm interested in trying to do, and I think is an important discussion to have if we really want to get to this idea of simulating sort of everything in the world. And finally, there are basic scientific questions about how we model super complex materials. One of the reasons you tend to see the same sorts of simulations over and over again in computer graphics papers is that we're still learning how to model all the material complexity inherent in the world. And addressing this challenge is incredibly difficult. It's not just a software problem, it's a hardware problem. But I think tackling it is going to unlock a whole world of new ideas. In the same way that sort of computational photography took off with the proliferation of photographic data, I'm sort of hoping for a similar renaissance for physics simulation and physics-based animation. So those are the big technical challenges. And there's one more challenge that I think it's important to mention, and that's the ethical challenge here. I don't think you can give a talk anymore about creating hyper-realistic virtual worlds or using simulations to test and validate critical devices without mentioning the ethical concerns. And I just want to highlight the work of Theodore Kim. He's an expert on simulation and animation at Yale, and he's already sort of sounding the alarm on many of these issues and drawing attention to the biases inherent in particularly to character animation that arise from our non-diverse set of models for things like skin color, hair, and other things. So I'm not an ethicist, but as a practitioner and a research in the field, I think it's important that we acknowledge that these issues exist and that we work with experts to help understand them and potentially alleviate them. And I'm confident that if we keep plugging away at these challenges, we can slowly move from some delightful squishy penguins falling down some inclined ramps to realizing this sort of emergent goal of physics and graphics that was articulated 3 decades ago. So I'll just finish up by thanking you all for coming and listening. I hope you found this at least somewhat interesting. I'll just end with some shameless self-promotion, and then I'll turn it back over to the organizers who are doing a fantastic job. Thank you, everybody.
All right, thank you, Dave. Thank you for giving this great talk. And actually, I have to admit, I'm one of those students, like you just mentioned, who have been suffering from parameter taking and those weird artifacts. But meanwhile, it's just so satisfying to say things finally work after getting over like all of this weirdness. So yeah, since we still have like 5 minutes, we'll just start our joint Q&A session as usual. And if any of you have any like follow-up questions, feel free to post it on the Discord, and I guess the speakers will be very willing to answer them. Okay, so the first question is for Michal. And okay, so sometimes the glossy materials feel smooth and matte materials feel a little bit rough. So we just wonder if it's possible to reproduce the bumpy textures associated with like this type of finishes.
So this depends on the way that the material is created. And there are either geometrical ways or material-based ways. So in the geometrical ways, even the varnishes themselves that have the particle structure, the individual particles as the varnish evaporates end up on the top and create the surface that you can feel with your finger, and you can feel it being physically rough. On the other hand, it is also possible to include particles which are just diffusive. So as they are inside your material, the material is perfectly flush. But since the particles are diffusive, you don't see such a strong reflection from a single point, and you see a nice matte surface as well. So essentially, there is a possibility to tune your haptic behavior together with the visual one just by selecting a proper mixture of these particles.
Oh, okay, that makes sense. That's a great answer. And also, okay, another question is like for Dave. Actually, there are 2 questions about eigenfit. The first one is like, because you just mentioned like with eigenfit, we can actually, I mean, like get similar visual effects like on coarser mesh. But I just wonder like, what's the price? Is it like still efficient? Because it's like, yeah, because like the discretization is like coarser.
Yeah, that's a great question. So there is a performance cost. Eigenfit is not as fast as doing the raw coarse simulation. Essentially, there's a little sparse eigenvalue problem that gets solved each iteration. Mm-hmm. It turns out that that's not too bad. I guess the real thing that I should say about eigenfit is that despite the fact that we're doing sort of a more general correction every time step, now, and this produces better results. It's not perfect. And so, if you have a look at the paper, you'll see that there are definitely like very nonlinear motions will still throw it off, and it still has trouble correcting for certain material models. And, additional physical effects, things like plasticity or tearing, these are still sort of unanswered questions. So I think it's like it's a big step towards doing the right thing, but it's not a panacea yet. Actually, my master's student, Honglin Chen, had a follow-up recently, which was more geometry processing focused on chordal sparsity. And she did this with Alec Jacobson and one of the illustrious organizers of this colloquium, Derek Liu. And here they have sort of a more optimization-centric approach, which is potentially going to work even better for simulation than EigenFit did, although we didn't sadly get to try it out.
I see. That's super cool. And we have a question related to this is like we wonder if it's possible to fit like a polynomial or even a neural network to get the mapping from like this coarse eigenvectors or say like the eigenvalues to the fine ones, as you just mentioned.
Yeah, I mean, I think like these kind of learning approaches are really promising here. I guess, I'm not a machine learning person really, so I don't know what works well and what doesn't, but the thing that I'm always interested in learning is that, essentially the material models we have now, they're already just, a lot of them are data driven. They were curve fits done by material scientists, right? And we figured out the parameters for those curves that give you the material behavior. And so using things like neural networks to represent these constitutive models is something that a lot of people are interested in. And I think is a great way to move forward, to sort of automate the material science side of this a little bit. So, it's a great question. I think rather than go after the eigenvalue mapping, go straight to the source. Go after, building the constitutive model itself. And, maybe build in like an extra parameter for mesh resolution when you do it, right? You have that flexibility when you have with a more expressive mapping. So I think it's a great question. I think, I would just say like, you have the opportunity to swing for the fences with that one.
I see. That's pretty cool. I mean, it's cool to know like there's some potential to like we actually get those like insights from the physical model itself. So yeah, another question for Michal is that, have you ever considered to extend this system to an anisotropic BSDF?
That's a very good question. An anisotropic BRDF would be kind of the one potential next step. And the tricky part is that the varnishes are all isotropic. So to this extent, if we would like to push the boundaries, we would either have to include the geometric modifications, or we would have to work again with the printer and improve the printing hardware to be capable of printing some anisotropic materials. So to this extent, there are some related works that were including metallic flakes and then orienting them with magnets into liquid media. And this would be actually quite nice for our printer because it can handle very large particles. So it would be very likely possible to jet also these metallic flakes inside. And the other alternative to include the geometry again is a little bit trickier one. And the reason for that is that there is, of course, a price to pay for everything. And the price for being able to handle very viscous materials and large particle sizes is that we have very large droplets compared to an inkjet printer, around 4 or 5 times larger. So also then our capabilities of modifying the geometry end up being essentially lowered by that. So we were thinking about it, and the most likely scenario seems to be including yet another kind of particles into the varnishes.
I see. That sounds very promising, and thank you for the answer. Okay, so we have like one last question for Dave, which is kind of like a big question. We just wonder, like, what do you think like the next 20 years of physics simulation will look like? Wait, Dave, you are muting yourself.
Oh, 20 years, that's a long time. I don't know, I guess, like I always sort of take my inspiration from science fiction. I guess, my science fiction is now quite old, but for people of sort of like my generation, the signature version of this is the Star Trek holodeck, right? Where basically like the simulation is essentially perfect. Every interaction between any object is simulated, and it looks and you perceive it to be realistic, like real, right? It doesn't take you out of the moment. I'm sort of like more interested in sort of the next 2 years actually, because I keep seeing all of these great things that are getting put into game engines where, you know, games are becoming more and more interactive. You're being able to interact freely with more and more of the world. And so it sort of feels to me like the acceleration is happening now all around us in terms of improving the interactive and emergent behavior in virtual worlds. So, you know, maybe like it's hard to imagine the next 20 years when you think that the next, you know, the next 5 years, the next 2 years is going to be so explosive. The other thing that I sort of on the graphic side, which is not a big problem, is not sort of a big problem for society, but is an interesting artistic problem, is I'm hoping that sometime in the next decade, someone will actually be able to formulate a mathematical model for cartoon physics. So, you know, all of this exaggerated motion that we do for VFX and cartoons, we're essentially forcing a model that was built for our universe onto the cartoon universe. And I'm really excited to see if someone can figure out, you know, what the differential equation is that governs like Looney Tunes or some of these other wilder interpretations of the rules of physics. That's sort of like my silly thing that like I think someone will figure out, and I'm excited for them to figure out in the next few years.
I see. I mean, that sounds great. We are looking forward to like seeing like such like efficient and robust and also like widely applicable like physics engine like appear in the next few years. And okay, so we thank like both speakers today and also like our artists like for this week's poster, which is just like truly brilliant. And see you all next week for Professor Ala Sheffer and Jose Sato's session next week.